start with, I'll just read a statement. So these events are being recorded and will be live streamed on our iQuest YouTube channel. For bandwidth purposes, we request that you please leave your videos off and your microphones off until the end. If you have questions during the presentation, I'll watch the chat box and we'll interrupt at the appropriate time. But at the end, please feel free to turn your video on and contribute to the discussion. Okay. So with that, so it's our great pleasure to have Cindy Regal joining us virtually. So like many of us here, Cindy Regal did her PhD in Boulder at JILA, and she worked with Debbie Jin, who Brian and I also worked with. She worked on atomic Fermi gases, also like Brian, and won the Daymont Thesis Prize for that work. She then did a brief postdoc at JILA with Conrad Leonard before going to Caltech, where she worked with Jeff Kimball as a Millikan postdoc. She then came back to JILA and Boulder in early 2010 and has done incredible work since then, both in hybrid systems and quantum optomechanics, and also single atoms and scaling to larger systems, which has helped kind of kickstart the recent flood of activity in that direction. So she's won countless awards, too many to mention, including the PCASE Award, the Packard Fellowship. She was a Hertz PhD student and won the Hertz Award for her PhD work. So with that, please join me in welcoming Cindy. And Cindy, please go ahead.
Great, thanks a lot, Jake. It's great to be virtually in Illinois, and I look forward to chatting with people more throughout the day. So what I'm going to tell you about today is going to focus on our work in quantum optomechanics, and I'll try to tell you a story about both quantum interferometry and our work towards quantum transduction using this platform. Okay, there we go. So the platform that I'll be talking about today is a microscale mechanical object that we use, which is really a drum-like membrane that vibrates like this. And we can probe it with light, as sort of visually shown here. And it is really micro scale. You can see it with your naked eye, this sort of thin film stretched across a silicon frame. It's about 0.5 millimeter in size. And this silicon nitride drum, we can push on it with radiation forces, and we can also detect its motion very well, as we'll talk about throughout this talk. It's really a harmonic oscillator, this mechanical object, sort of nothing more than that, coupled to another harmonic oscillator, which is the optical field within this cavity. But nonetheless, there's a lot of rich physics that we can talk about in this cavity optomechanics system in the context of interferometry and in the context of transduction, as I'll talk about today. In many ways, this harmonic oscillator is similar to many other quantum systems that you might work with and control their motion, such as trapped ions. The distinction with these solid state objects that I'll be discussing in this talk is it's really an elastic deformation of many atoms, but yet still a single degree of freedom. It's this microscale size, which will have important implications for the type of quantum physics and technology that we can pursue with these devices. And again, they're fun because they're somewhat large. The mass of these objects is about 10 nanograms. So maybe to give a little bit of a backdrop first, of this general field. I was told that this was a quantum colloquium to a wide variety of people and audiences within quantum, which I've come to learn means a very wide range of backgrounds. So I'll give you a little bit of sense of this field of mechanical systems and bringing them towards a regime where we can study them as a quantum system. And these ideas sort of popped up around the early 2000s. The idea that you could take a micromechanical system, an engineered microfabricated structure, and try to bring it to the quantum regime. And there may be two enticing possibilities. One, you could make very high frequency mechanical objects and at temperatures that you get to, and for example, a dilution refrigerator, you could be able to bring that object to its ground state and probe it. You could also think of floppy or lower frequency objects and doing things that were akin to laser cooling. And we really like laser cooling things in Boulder. So it's a type of thing that fits in there well. And there were a number of experiments that pursued sort of both of these types of ideas. And today there are many engineered mechanical systems that really can be brought to the ground state in both of these directions, both via these laser cooling type prospects, as well as experiments that basically directly cool the objects. This field is quite rich because it has a number of different connections to different areas. For example, trapped ions, where one looks at the quantum motion of the ions in their trap, has long been a mechanical system that is interesting to study. And many of the experiments with these larger objects look to those experiments for inspiration. There's also connections to quantum measurements of large test masses, which is an area of study that's been around for a long time, since the inception of quantum optics. And this is one of the connections that I'll talk about today in this talk. So one of the things that you might have seen within the context of this field in the recent decade or so, and in a number of papers out only in the last couple of years, is with these mechanical devices, especially by coupling these mechanical harmonic oscillators to two-level systems associated with superconducting qubits, people are now able to really count individual phonons of the mechanical excitations using superconducting qubits and do tomography on that motion, for example, which is a very interesting regime of real quantum mechanical motion. In this talk, I'm going to be focusing on a bit of a different aspect of these optomechanical systems, which is a little bit more on the sort of interface between the light and the mechanics. So a lot of the early ideas of the field were to use light or electricity to control mechanical motion, say cool it to its mechanical ground state. And although it's the same interaction, the talk today will focus a little bit on the flip side, which is using well-controlled cold micromechanical motion to control light and electricity. And I'll talk about this from a couple of different perspectives, which will hopefully help bring some different types of ideas within measurement and transduction together. So I'll talk about a number of things in this talk. So first I'll talk about interferometry and quantum measurement history in the context of optomechanical systems. I feel like this is a good introduction to the subject. We'll sort of be here in what I call the land of Gaussian states, basically dealing with squeezing of light, for example, but it's a good example of pristine mechanical and optical control within the context of this system, where I have a mechanical object coupled to an optical cavity in the presence of radiation pressure. I'll segue from this into some ideas that then take this interface between light and mechanical motion and extend it to making quantum transducers with our work towards connecting superconducting quantum bits and their quantum states to optical signals through micromechanical motion. And this is a collaboration with Conrad Leonard at JILA. And then I will end by talking a bit about the intricate micromechanical motion design space that we work in that's making these mechanical objects even more and more coherent with helps with all of these different quantum things that we would like to do. So again, as I mentioned earlier, I'm trying to try to keep this at a pretty broad overview-y level in terms of telling you about these transducers and different ways that we can study quantum measurement in optomechanical systems. And if you want the latest numbers or interesting things that we've added to our quantum transduction experiments, I'm going to show, for example, some archive links that'll give you those latest numbers, but I'll try to keep things at a pretty broad level. Okay, with that, I'm going to start out by telling you a bit about interferometers and thinking about quantum noise and how we can measure those type of things in our micromechanical system. So to do this, I find it actually helpful to start with a very simple interferometer, say a Michelson interferometer that everyone is familiar with, so from some early lab course. where I take a laser beam and I split it between two paths, and I can tell something about the differential motion of these two objects by looking on a photodetector at this fringing pattern that I see, which will vary at the λ/2 scale. And if I sit on the side of this line, I can monitor the differential displacement of these two objects. And this Michelson interferometer is a common measurement tool for, as I said, everyday tasks and also heroic tasks, such as LIGO, for example, in searching for gravitational waves. And the point that I want to make here a bit is about what is the limit of the signal to noise? If I were to just think about how well I can measure the position of an object in a Michelson interferometer like this. And one of the limits that I could get to is a case where the shot noise of the Poisson distributed photons of the optical field that I have when I'm sitting on this fringe and measuring are one of my limits to the signal to noise, and that'll go as the square root of n. Now, there's another limit that you could think about where now this interferometer, you can think about these masses that you're measuring as no longer immutable. They're objects that I'm now drawing them as masses on a spring. And in the context of, if I think about large amounts of laser power inside of this interferometer, I can think about the light pressure on the mirrors being important, the radiation pressure of the light. And this was first thought about, for example, in the 1970s by Vladimir Briginsky in the context of instabilities in such an interferometer. But you can also ask whether in this limit there's an effect on the signal to noise in the context of measuring the motion of these test masses. And indeed, the shot noise of radiation pressure will be important in the measurement of those test masses. And you could think of that as like little bits of red balls, bouncing down and randomly impinging on these masses. And what this ultimately imposes is something called a standard quantum limit within this interferometry problem. And there's many standard quantum limits, and they are not necessarily all limits, so it gets a little bit confusing, but I'll tell you the basic idea of this one. If I do a back of the envelope calculation of how well I can measure this test mass, I'm considering myself maybe in the free mass limit, where it's a time small compared to an oscillation period. And also keeping in mind to measure, say, a passing gravitational wave, I would have to measure that object more than once. So if I measure that object to some delta x, measure at some time t, then I will end up with some, in this back of the envelope sort of perspective, a momentum uncertain to some delta p perturbed that's inversely proportional to that delta x. And so at some later time, I end up with a combination of uncertainty due to that initial position uncertainty and something inversely proportional to it that also has h bar and some characteristic timescale. If I balance this imprecision and this backaction, I get this standard quantum limit that again depends on h bar and a mass and a scale of a time. And so this was considered in the context of early thinking about gravitational wave detectors and quantum optics. There's a early paper by Carl Caves about quantum mechanical radiation pressure fluctuations in an interferometer. And so experiments that we can do with these micromechanical systems are looking at things like this interesting quantum measurement problem, where you're in a system where you can easily look at radiation pressure effects in a micromechanical regime. And in this regime where you can get to where you can have a dominant force due to the shot noise, it's an interesting starting point for making squeeze states of light in the context of these experiments, which is one of the things that I'll talk about. So let me move on from that bit of context and introduction to our optomechanical system. So I've been showing this cartoon, which is our optomechanical system, which is not a Michelson, it's a Fabry-Perot resonator, but a lot of the same contexts apply. And as I said at the beginning, we work with silicon nitride membranes, which are drums that are very thin, about 50 nanometers thick. They're very highly tensioned, a gigapascal, so that the resonant frequency of these objects is really 3 orders of magnitude larger than it would be if it weren't a stressed film, which makes it very much a drum. By sort of cranking up that oscillator energy with respect to keeping dissipation about the same, you can get very high quality factors with these objects, 10 to the 8 scale, even at room temperature. And for some scale, the 0-point motion of these objects, which is about where we probe, is about a femtometer. So we put this mechanical object in the middle of a Fabry-Perot cavity, which makes an effective sort of moving mirror in the context of the system as that dielectric wiggles inside the standing wave of the cavity. And typically, all the signatures that we look at in these experiments are looking at the phase quadrature at the output of the cavity system and monitoring the motion of the objects. So looking at a displacement spectral density as a function of frequency. And here's an example of looking at Brownian or thermal motion near the mechanical resonance, which is at about a megahertz scale. So in these experiments that we do, we work very much with cryogenic systems in order to pre-cool these mechanical objects. So we do a combination of this cryogenic cooling as well as these sort of laser cooling concepts that I'll talk about in a bit. But let me give you a sense first of what we do when we cryogenically cool these objects. So this is a person working on the optical system, which is inside of this copper box. Here is the cavity, and it's on a stage of a dilution refrigerator that has a free space optical port. So we can do very JILA-esque standard cavity measurements, but in this quite foreign cold environment. And so we can send the light into the dilution refrigerator and out. This is a little bit of a close-up of the copper box that the cavity lives inside. And the nice thing about these experiments is, somewhat surprisingly, these micromechanical membranes thermalize to about 80 millikelvin, even with a very large amount of light at about a micron impinging on them inside these Fabry-Perot cavities. We've even expanded our capabilities to do cold measurements of optomechanical systems in recent years. So this is our very latest dilution refrigerator. It's from Blue Force that will allow us to also do these types of measurements in a closed cycle system that we can hold for a while to have low vibrations. And this is in the same lab as these other devices. So one of the things that we're looking at in the coming years is really having a fiber link between, say, a cavity optomechanical system here and one over here, and especially if we turn them into interesting electro-optic transducers, as I'll talk about later. This can be a way to look at networking between superconducting qubits. So the other idea that we use in the context of these experiments is something akin to laser cooling, and there's many ways to look at this optomechanical interaction, and I'll show the sort of laser cooling one here so you can get a sense of this physics. But basically, if you're familiar with, for example, laser cooling of atoms, this is a good way to think about this interaction. What we can do is optically damp and cool the mechanics with a drive that's red detuned of the optomechanical cavity response function, as shown down here. So if we do this, what we can do is we can enhance an anti-Stokes process over a Stokes process, and we can actually do optomechanical cooling and damping of our membrane mechanical object. And we can also get information about how cold we are by looking at a sideband asymmetry, similar how you would use Raman spectroscopy, for example, with trapped ions. So if we do this, we can look at the phonon occupation as measured via this calibrated sideband asymmetry as a function of the optomechanical damping, and we can see how well we can cool our object. These are little cartoons showing the sideband asymmetry that we observe and how it tells us about the mechanical temperature. So the damping range that we can get in these experiments is quite large. It's sort of like 10 to the 4 dynamic range, which is related to the very high Q of the mechanics. And we can cool to below a phonon, reaching about 0.2, which is about 80% ground state occupation. And the limit here being the sideband resolution of our cavity, which I could think of in some analogy to the Doppler limit in the context of atomic physics. Okay. But the amount of sort of extraneous heating above this expected sideband resolution limit is fairly small, again, indicating this idea that we can put a lot of light on these micromechanical objects and have them still be cold. And some way to think about the general requirements for being in an interesting quantum regime in the context of these optomechanical systems is to have optical measurement rates or photon-phonon exchange rates with a propagating field to be large, compared to a thermalization rate with the mechanical environment that you want to be slow. And this first is related to, as usual, some sort of coupling, a photon number pump enhancement, and the cavity damping. And then the thermalization rate with the environment is really related to the initial phonon occupation, as well as the mechanical quality factor or the mechanical damping. So in all these types of experiments, one can work hard to make types of mechanical objects and types of cavity couplings to make this ratio large. So getting back to this idea of measuring the standard quantum limits in the context of these mechanical systems, one way to look at this in the context of, say, measuring spectral density of fluctuations as a function of measurement strength in these optomechanical systems is that when you're probing weakly, your imprecision or shot noise limited, but eventually you'll be limited by the backaction from this radiation pressure combined with the shot noise. And when you're on resonance, the point where you reach the standard quantum limit, you will have these fluctuations on order of the 0-point motion. So this radiation pressure and shot noise, or the amplitude of the light driving the mechanics, and then actually writing back onto the cavity or the phase of the light, can lead to interesting dynamics in the context of this concept of the mechanical system actually affecting the state of the light. And one way you can describe this is a phrase that's been around for a while as ponderomotive squeezing, or mechanically mediated squeezing of the light from the optomechanical interaction. So this is something that we can see in our experiments if we set up this membrane cavity optomechanical system and do something to rotate the quadrature. So we mix amplitude and phase, and we're able to use these correlations between the phase of the light and the amplitude of the light from this radiation pressure to actually get squeezing of the light only from the optomechanical interaction. This is a movie sort of showing the noise appear below shot noise for some region of frequency space near the mechanical resonance. And for the most part, the shape of this noise is as expected from the cavity optomechanical interaction. And we can see a little bit of squeezing here. In our experiments, the amount of squeezing is defined by the efficiency of the measurement. In some other measurements, we measure a scale of 3 dB of squeezing. Another thing you can see here, though, is that there's one region of the spectrum where the spectrum doesn't follow what you would expect from a simple cavity optomechanical system. And this is actually due to what I would call an imposter mechanical mode, not just the simple mechanical mode that I've been showing you that's perfectly isolated. And there are ways that we can mitigate these types of effects, and it's an interesting design space that I'll talk about later. So one way you can think about, the squeezing and what is it useful for, it's very much benchmarks a bit these optomechanical systems in terms of efficiency of measurement. Measuring squeezing is a very honest way to say how efficient you're being. But it's also interesting to think about in the context of some of these historical questions of how well can you measure mechanical motion in the presence of backaction in what different types of regimes that people have maybe historically cared about in the context of broadband displacement detection, which I might do, for example, on a gravitational wave detector, or on resonant detection, which I might do in sort of often more of a small scale sensor. So it's interesting to understand some of these limits, and this is a bit of a illustrated guide to these ideas of broadband detection and some of the things that we can play with the quantum noise. So this is plotting a position spectral density as a function of frequency detuning from a mechanical resonance on a log scale in a limit where the backaction on resonance is quite a bit bigger than the 0-point motion. So this is in sort of the strong measurement limit. And if I think about a typical homodyne measurement of the output of the system, so I measure in the phase quadrature, the best I can measure is sort of shown by this blue dashed line here that adds up these different contributions. And the standard quantum limit in the context of measuring at multiple Fourier frequencies can be thought of as if you optimize the optical power at any given frequency, you can get to this standard quantum limit. What you'll note in this regime over here is not equal to the 0-point motion of the mechanical object. It's actually larger. And in this regime, you can sort of think of it as your phase detection in a homodyne detector is not optimally set up to measure this 0-point motion of the mechanics. So it gets a little bit beyond that sort of back of the envelope calculation from before. The sort of quantum limit for making a two mechanical quadrature measurement would be more what's shown by the black line. So we can play in the space between the standard quantum limit and this mechanical limit here with this type of squeezing interactions. And one way you can do this is actually using the ponderomotive squeezing itself by rotating the quadrature that you measure at. This idea that, well, maybe the phase quadrature isn't the optimal, I should go to, at any given frequency, some other quadrature to measure in order to measure better. And you can see, indeed, you can get below the standard quantum limit by measuring in these different quadratures. And you can even imagine schemes where you vary that quadrature as a function of frequency, and you can optimize over a larger range of parameter space. So these are some data from our membrane optomechanical system that show that we can set our homodyne detector to measure at different angles, and we can measure below what we would expect from having no ponderomotive squeezing in terms of less noise compared to that limit as a function of detuning from the mechanical resonance. So this is a way to study different ways that you could use these squeezing ideas in the context of doing better in an optical measurement of a mechanical system. And these types of things are, you can work in a micromechanical system, you can understand which quantum sensing proposals work, which are hard in the context of the particular platform. And these ideas are pretty broadly represented in a variety of areas. A recent paper looking at quantum correlations between light and kilogram mass mirrors of LIGO, both from injected squeezing as well as ponderomotive squeezing, even in the really large kilogram scale mirrors. So this interplay of radiation pressure and quantum measurement is an interesting space, and also is a very good benchmark of how we understand efficiency and noise in the context of these systems. So with that, I'm going to move on to the next subject, which is then talking about adding microwave components to these optomechanical systems to work towards transducers that make use of this efficient optomechanical interface. But if anyone had any questions at this point about the first part, it would be a fine place to pause.
Any questions?
Okay. Yeah, if not, we'll just keep going here.
Could I ask you just kind of a general question? I'm curious, so another type of optomechanical system, of course, is sort of a nano beam type resonator.
Yep.
And I'm wondering, back when you started doing this work, why this kind of membrane structure appeared more attractive, or what the differences might be between the two?
Yeah, exactly. No, I think that at the beginning there, I showed many different optomechanical systems, right? And there's nanobeam systems that are, have certain advantages and also are much more integrable and scalable in many ways. And there's electromechanical systems that are somewhat more compatible with cold environments. I would say that the membrane system is, I think there's very interesting aspects of all of them, but it's nice to study both directions. One of the reasons is the nanosystems tend to have a little more heating effects. They have much stronger interactions, but if you try to continuously optically probe them, especially with some of the piezoelectric materials involved, you can have more heating effects. And you can think of that as sort of a fundamental trade-off, right? The energy densities in those systems are larger because the couplings are just larger. And so like bandwidths of transducers can be larger. The membrane system is quite interesting from a perspective of, on the other side of the fundamental point is that the energy densities are low. So we can actually do this where we, there's hundreds of milliwatts of circulating power in these cavities, and it's a pretty pristine flat object, and it doesn't heat up at the sort of 100 millikelvin level. So that's one of the advantages of the membrane system. The other thing that I'll talk about as we get into the transducer, I would say these things where you can do ground state cooling and you can probe radiation pressure effects and you can look at ponderomotive squeezing, they've really been done both in the nano and the micromechanical devices. This is sort of a colloquial introduction. When it comes to the transducers, there is some fundamental differences of what I would say as separation of length scales. So with the micromechanical objects, we can put a microwave circuit 0.5 millimeter away from where the light is, and that is really quite different than what you can do with the nano devices. So I'll show some of that coming up.
Okay, thank you.
Yep. Yeah, sorry, there's a long answer telling you half of the next part of the talk. Okay. All right, well, great. Let me tell you a bit about this concept of using these micromechanical systems as transducers. And Jake gave a nice overview input in terms of his question, in the sense that these transducer type effects are also pursued in nano devices, as well as these micro devices. And there's different pros and cons of each of them. And I'll focus a little bit more on this micromechanical method. So the idea here is we have our optical fabric Rho cavity that can couple to this micromechanical motion, and we can read it out in light. And as you've seen from the previous part of the talk, we can have an efficient interface and measurement, as evidenced by, for example, being able to do squeezing, which is the optomechanical system. And in these experiments where we make a transducer, we also couple our micromechanical object to a superconducting LC circuit. This is just a circuit, not a qubit. The qubit part would be over here. Create a quantum state, send it down a transmission line, and this would be a linear converter. Then that takes that quantum state up into the light. And you may say, well, a megahertz scale mechanical object seems like a bit of an odd intermediary in the context of these of a transducer, right? You're bringing it down to a frequency scale that in principle is perturbed by the thermal environment of your system, I mean, even if you cool it to a dilution refrigerator. But part of the earlier part of the talk was a little bit of a preface sort of saying that these micromechanical systems, even though they're at a megahertz, they can be very well isolated from the thermal environment that they're in a way that they really cannot operate as a quantum intermediary, or at least we think that the parameters are there. So the idea of making a transducer that could take quantum states from a superconducting qubit and bring it to the optical domain is being pursued in many different contexts. And the idea being that you could have many quantum nodes. This illustration from MPQ is nice, and that you could have optical fibers as the quantum connection. And in the context of superconducting qubits, we think of it a little bit as the interesting quantum states are stuck in the bottom of a dilution refrigerator, and you have to get them out into light in order for them to transmit over very long distances over fiber. Although there's certainly interesting experiments people are doing with long niobium cooled cables, right? There's many different alternatives. But this idea of taking a quantum state and converting it to light in the context of, for example, showing an entangled link is pretty much an unsolved problem in the context of the parameter space that would be needed for a large scale quantum network. And the idea is, not only could it be useful for long scale things, but it also could be useful potentially for interconnects, even within the context of a cold environment. So let me go over a bit. If we want to make a transducer that is going to be sort of quantum enabled, able to transduce quantum states from one domain to the other, what are some of the requirements that we have to consider or measure in our system? It should be bidirectional. It should be capable of a unitary transformation between these two domains. It should be efficient. In quantum systems, we always worry about a beam splitter in our system where noise leaks in the other port. And it has to be low added noise. So there's many other ways that noise can creep in to the system, and we have to quantify that as well. So maybe in a little bit even more context in the context of this transducer between electrical and optical domains for a quantum system, it's useful to note that an electro-optic modulator with a nonlinear crystal, which if you work in an optics lab, they're all over your table, right? You use, say, lithium niobate modulators for a variety of tasks, and they also could achieve the type of metrics that I'm talking about in these experiments. And there's been a number of works in these directions, both in the context of chip scale devices and also in the context of large scale devices, and some very interesting recent results down here in this archive paper. But there are some advantages of the optomechanical electromechanical systems over sort of a crystal that you pull out of the drawer. And I like to think of using mechanical motion as sort of a way to engineer a nonlinear material. For example, the squeezing example that I showed earlier, you can think of the optomechanical system as a Kerr medium, an intensity-dependent index, because as the intensity changes, you get different amounts of radiation pressure, and your mechanical object moves, and your effective index moves. So by using mechanical motion to sort of engineer the nonlinearity, you have a certain flexibility in materials and geometry and size. And in the transducer that I'll talk about today, one thing that's nice about it, in addition to this sort of large size scale that allows us some flexibility in taking these two disparate things and putting them together, there's also the fact that we don't really require any special materials. There's no piezoelectric materials. It's just a slab of dielectric. Okay, so let me tell you a little bit about what this structure looks like when we turn it into a transducer. And I show Konrad Lehnert's picture here to emphasize that his group makes these micromechanical electromechanical devices that make this coupling between an LC circuit and these membranes. So the idea in our transducer experiments is we take a membrane mode, much like the ones I was telling you about at the beginning of the talk, and we also put a piece of metal on top of this mechanical object that's a very thin film of niobium, or in more recent experiments, niobium titanium nitride. And this modifies the modes a bit from the ones that I showed you earlier, but they have a very similar character and are also scale of megahertz. And as I was talking about earlier, one nice thing about using this mesoscopic or micro object is a spatial separation of the probing. We have our optical spot over here, and then we have our electrical circuit coupled over there. And we actually couple to an electrical circuit with what we call a flip chip device. So we have a top chip that has this membrane and the little capacitor pad here. And then we have a bottom circuit that has an inductor loop. And we flip them on top of each other so that these two plates are separated by a couple hundred nanometers. And this makes our electromechanical circuit. We then take this whole electromechanical circuit and put it inside an optical fabric Perot cavity, similar to the ones I was talking about at the beginning of the talk. And the whole device looks like this. It's a very macro-ish device. It has a microwave port, that's the SMA connector here, and it has an optical port, which has a hole shown on the side there. So the type of interaction we use for this system, it's a sort of double parametric coupling in the case of our particular transducer. And this double parametric coupling, we pump the electrical circuit red detune to introduce this photon-phonon exchange rate, a beam splitter interaction. And we also pump the optomechanical circuit red detuned as well. And then what we're transducing is some signal that is detuned from those pumps by the mechanical resonant frequency. And one way we can think about the properties of the transducer is just to think about a two-port network and think about measuring S parameters, say on a network analyzer. And in that context, the S parameter that tells us about the transmission in either direction is going to be dependent upon these optomechanical and electromechanical coupling rates according to this equation here. And we want this to approach 1, so we want it to be efficient. And in a limit where we can impedance match, where this optomechanical and electromechanical coupling rates can be equal, that's the limit that we will get full transduction between the 2 different domains. And you might expect that given the difference in physical platform of these 2 different types of coupling here in the electrical and optical domain, that impedance matching could be hard. But it turns out that the parameters end up very similar in terms of what we can get these gamma rates to be. So let me show you some data about one of the very nice features of this particular transducer that we've been able to work with for a while. These results are showing you these scattering parameters measured on a device from a few years ago from this paper here. And what we're looking to start with is the reflection off of the electrical port, the gray trace being with the transducer off, and then the blue trace being with the transducer on. And we can see that reflection goes nearly to 0 there. And in return, we get some transmission of the signal through this whole electro-optomechanical circuit. And we can see that we get an analogous effect in the other direction. These are actually data, network analyzer type data, and you can see that it's working identically in both the sort of up conversion and down conversion directions. So the nice thing about this interface is this transducer box that we're working with is nearly 50% efficient. So it's the most efficient of any current electro-optic transducer platforms that are out there. So this is a nice feature of the system that really has to do with being able to engineer all of these components. Another nice feature of our transducer is if you look deep into the noise of the circuit, which is what we spend a lot of our time doing, we actually find that the laser light does not cause the problems that would, say, preclude quantum transduction in these types of experiments. So it doesn't cause the LC circuit to have noise due to the laser light at the types of powers that we need at an appreciable effect. So this is a nice advantage of a micro device, and somewhat surprising in the sense that these superconducting circuits are very sensitive to any amount of optical photons that would impinge on them, create quasi-particles, create noise. The main thing that is the current limit of these transducers that we work with is the added noise. We're making it ever smaller. A number of years ago, it was around 10, and we pushed it even lower in recent experiments, but it's not yet a quantum interface from that one perspective. And we can quantify this added noise sort of by just listening at these ports to different noise processes that are going on within the context of the whole device. And I'll tell you a bit about what some of those noise processes are and refer you to a paper of some of our very latest numbers. So some key noise sources are mechanical thermal noise can be a limit in the context of putting this entire circuit together and asking whether we can really get high enough Q mechanics. And I'll show you in a moment some ideas that we've used in recent experiments that have really been able to get rid of mechanical thermal noise as a limiting factor. Circuit noise, due to this interesting flip chip device that we're making, which is actually quite an interesting geometry and types of materials that we're using, does end up being one limiting factor of the noise of our transducer. Some of the recent things that we've been doing, we have added recently a superconducting qubit as an additional module in this system. And I refer you to this archive paper if you want to read about our latest parameters and introducing this superconducting qubit into the system and doing non-destructive optical readout in that context with the transducer that has some amount of added noise, but is really quite a good amplifier that is read out optically. We're also working to introduce single photon counting in these experiments. All the types of measurements we've done so far are in heterodyne detection at the output of the optomechanical or electromechanical system, but we should be able to do photon counting by also filtering the optomechanical pump. So with that, that's a bit of an overview of where these transducers are, and I'll be happy to answer questions about that. In terms of this mechanical thermal noise, let me give you a little bit of a sense of the types of things that we can do with these mechanical systems to control that thermal noise that have been incorporated in recent experiments, but I'll show you their basic concepts. So when I showed you these experiments early in the talk where I showed this particular mechanical mode that we're always using, there are many modes of this mechanical membrane, and we tend to use this one because of certain aspects of how we can probe it. But you can ask, there should be a whole other forest of modes, and how do we get a clean spectrum with just this one mode that we can focus on? And in the sort of modern iterations of this where we've done this well, what we do is we create a band gap in the acoustic spectrum near this megahertz mechanical object in order to create this clean mode spectrum. And the way that we do this is by introducing a periodic array of masses around this membrane object. And this has been done in a variety of nano devices as well. I cite one paper down here that pioneered that area. These devices maintain the membrane here and then have this periodic array of silicon masses. And with these devices, for example, we can see very large quality factors of these few megahertz membranes, as well as this creating a band gap in the acoustic spectrum. These are data showing that at these megahertz scale mechanics, we can see ring down times that are scale of a minute at cold temperatures. So this is the type of phononic isolation that we've incorporated into our transducers to avoid thermal noise concerns as a noise factor there. But there's also a variety of other phononic structures that we're looking at, not only to our transducers, but also different types of sensing experiments. For example, we're looking at spin sensing harnessing these particular objects. And here you can actually pattern the silicon nitride itself. So the gray holes here represent where there's no silicon nitride, and the gold part is there is silicon nitride. And there's a defect mode in the center that looks like this, and you can optically probe it here. And you can say it softly decays into the silicon nitride substrate. And this was pioneered in Copenhagen. And we can make a variety of different structures. We've worked on some very localized structures here with some very large mass ratios for the phononic crystal. And we can make more and more interesting structures that isolate certain defects. This is showing a forest of modes outside of the band gap and a very clean band gap in the context of these structures. We can also move this defect mode around. For example, our most recent structure, we call it the snowflake. It looks like this. And it has a particular localized mode and all of these other tethers to put the defect exactly where we want with respect to the band gap that's defined by this periodic structure out here. So these are fun structures to play us that are really pushing mechanical coherence. And these very tension membranes make an interesting platform to make these structures. So with that, I think I will end there by pointing out our collaborators at JILA, Conrad Leonard and Theodore Graham-Smith, and then many people who have worked on both these optomechanical experiments as well as the electro-optic combination over time, and are continuing to push on the transducer parameters. So thanks for your attention and happy to answer questions.
All right, thanks, Cindy, for an excellent talk. Any questions? Okay, so one question I have, I guess, so with this relatively low bandwidth, so you have very high conversion, but the bandwidth is roughly megahertz, is that right?
So the bandwidth is even smaller than megahertz. It's currently kilohertz, which is small. Yep.
Okay, so if you do kind of a long distance network where you do Hongel-Mendel type interference to herald entanglement, would you, I guess you'd be quite sensitive to path length and like phase shifts, and you may actually have to correct that somehow. Is this a problem you've anticipated?
Yeah, so let me talk pretty generally about this bandwidth and ways in which it's potentially an issue, but potentially also something that's pretty reasonable for where superconducting qubits are. So if I think about typical bandwidths that would be relevant for, say, a transmon superconducting qubit, tens of kilohertz is not so far off in terms of where you need to be. So from that perspective, it's not uncrazily matched. And if you go to this archive paper, we talk a bit more about that matching, which is not there with a kilohertz of bandwidth, but with tens of kilohertz, it is a possibility. And then, yeah, in terms of, obviously bandwidth is everything in some ways, in the sense that it feeds into a sort of a bit rate that you could end up having. But there is sort of two things that matter for that bit rate. One, whether you can operate your system continuously with everything staying alive, and then the overall, what is the absolute magnitude of the bandwidth? So for example, with lithium niobate or with nano devices, certainly the bandwidth will be higher, but there's also a question of duty cycle. So if I were to sort of plug, what are the advantages of this particular system, and how do the numbers actually sort of reasonably work out? The tens of kilohertz bandwidth for connecting transmons and doing initial experiments, heralding experiments, is a possibility. And in terms of bit rate, being able to operate these systems continuously, I think is actually quite an advantage.
I see, that makes sense.
I have a just broad question. I saw your recent paper on using these in the search for dark matter. Could you briefly talk about that?
Yeah, good question. So yeah, there was a Moore Foundation workshop that happened a little bit pre-COVID, where people came together, sort of from large-scale detector community and also micromechanical community, levitated objects community, and asked, I would phrase it in that context a little bit more as, could accelerometers be useful in the context of dark matter searches? And as you know, there are many dark matter candidates, and there's many ways to think about how different detectors that are sensitive could be important for that. And one of the questions on a grand scale, when you ask, what makes a really good accelerometer, usually it has pretty big mass, right? But also the frequency range matters, many different parameters. And then there's also a lot of questions about, well, if you really want to push the sensitivity and you run into the standard quantum limits, how do you go beyond that, right, is another general question. So, I think that the question of how you would use accelerometers or optomechanical systems, or techniques to go beyond quantum noise limits to search for dark matter is, I would say, a fairly open question, but that's the type of thing that we were trying to answer in that workshop.
All right, other questions for Cindy? All right, great.